Hello everybody, welcome back to my channel. Today we're going to talk about blending problems or mixing problems, right? And the idea is, I think there are essentially two kinds of blending or mixing problems, and I want to explain to you what the main difference is and what that means in terms of selecting the type of a model or variables you're going to need to use in this case. So you have a blending or mixing problem essentially if you are taking some inputs and combining them, putting them together to create one or more outputs. So I usually like to explain this with a picture. So let's say I have some raw materials. I have these buckets with things in them, right? This could be liquids or something solid. Let me call this material 1, 2, and 3. And I want to use these or mix them together to make some final products, right? Let's say I also am making 3 final products. Let me call them A, B, and C. So the idea is I can take some of this and throw it here and or here. Likewise, I could take the second raw material and use some of it to make the products. It doesn't have to be that all materials go into all products, but it's possible. And I also have a choice to use the third material. Oops, not twice in the same place. Third material to make the products. Great. So typically the question in these problems involves the following. Excuse me. You have some limited amount of these materials, right? You may have some required production amount for the products. And there could be a recipe involved. That is to say, you have some rules, okay, to make product A, you need the following things to happen so that product A is of sufficient quality, right? And I'm going to call this the recipe. Let me write that here. There's going to be some sort of recipe rules. All right? And there could be, costs associated with the raw materials and revenues associated with the products, and you might be, for example, maximizing profit. Now let me go back to the question of the recipe, right? I like to divide these problems into two kinds of recipes. What I'm going to call the fixed recipe and the flexible recipe. The fixed recipe is basically what you get when let's say you're making a cake, right? You're going to say, all right, for every pound of this product, let's say product A, you're going to need, so many ounces of material 1, so many ounces of material 2, and so forth. So that is to say, if I tell you how much product A I made, you can tell me exactly how much of each of the raw materials you used because the recipe is fixed, right? The other variation is when the recipe is flexible. I'm not going to tell you exactly how much of each material goes into each unit of the product you're making. The only requirement I have is as long as the final product satisfies some characteristics, I don't care how much you mix in of each of the materials. Let me give you an example. Let's say I am making orange juice, right? Let's say Minute Maid. Coca-Cola is making Minute Maid, and they do it by squeezing some oranges. But there are many kinds of oranges that you can be using. Each of them has a different flavor and acidity. Let's consider the pH of the orange juice. But Minute Maid, because of its characteristic flavor, needs to have a certain acidity, let's say, right? A pH of a certain value. When I'm mixing in my oranges, some of them have a higher pH or a lower pH, but the recipe could be like this. As long as the resulting pH of the final mixture of orange juices is equal to a given number, I don't care how much you mix of each orange. So notice, in that case, if I tell you, oh, I made 10 gallons of Minute Maid, you're not sure how much of each orange you squeezed in there, because the only requirement was as long as these 10 gallons have a certain pH, you're fine. So that is what I'm calling the flexible recipe. I am only given some rules for the final product, but knowing how much you made of the product does not allow you to tell how much you used of each individual ingredient. Okay? So in what way do these kinds of recipes affect the mathematical model? In the following way. If your recipe is fixed, I only need one variable per final product. Why? Because if I tell you how much A you made, you can tell me how much of components or raw materials 1, 2, 3 you used. If the recipe is flexible, to be able to do all the calculations I need in the mathematical model, I have to know exactly, let's say you made product A, I'm going to divide this by mixing some material 1, some quantity of material 3, and some quantity of material 2. I'm going to need to know exactly how much of each of those you put in there. So in a flexible recipe situation, I'm going to need one variable per pair raw material comma final product. Okay, this is the pair in parentheses. So let's say in this case I can mix any of the 3 raw materials to make any of the 3 products. There is a total of 9 combinations. How much 1, 2, 3 did you use to make A? That's 3 variables. How much 1, 2, 3 did you use to make B? That's another 3 variables. In total you have 9. If this problem had a fixed recipe for ABC, I would only need 3 variables, XA, XB, and XC. That is to say, how much of each of the products you made. Okay? This video will focus on the fixed recipe version of the blending problem. If you landed here but happen to be interested in the flexible recipe version, I am going to put a link up here so that you can click on it and you'll be directed to that video. Alright, now let's take a look at an example of a blending problem with a fixed recipe. Don't worry about the Excel sheet for now. Let's take a look at the problem first. Alright, Tropishine Company supplies fruit juice and juice blends to wholesale grocers in Florida. The firm's products and their revenue per ounce are shown below. So they make 5 products: apple juice, grape juice, cranberry juice, which is just like plain juices, and then 2 blends, the apple grape and the apple cranberry. And this is what the revenue per ounce is. Now, I said this is a fixed recipe problem, so the apple grape juice, how do you make that? It's 70% apple, 30% grape. So if I tell you how much of this I made, you know exactly how much apple you used, how much grape you used. Likewise, the apple cranberry has a recipe too. It is 60% apple, 40% cranberry. The 3 raw materials that they have are the pure apple juice, pure grape juice, and pure cranberry juice. Right? So 3 raw materials and 5 final products. You can think of the apple final product as me mixing apple with nothing. Right? So just take the raw material called apple juice, put it in a box, and call that the final product, whose name is also apple juice. Great. The only products that require mixing are products 4 and 5, right? The apple grape and the apple cranberry. All right. So we have some availability for the apple grape, and cranberry raw materials in gallons. So we're going to have to do some conversion between gallons and ounces here in a little bit. And the owner wants to know how many gallons of each product to make to maximize profit. So we were given revenue, and now we're going to be given costs for the three raw materials, apple, grape, and cranberry. The costs in cents per ounces are 2, 4, and 3. They already have some commitment, an order for 10 gallons of apple juice and 12 gallons of apple cranberry juice. So we need to make at least those amounts of those two products, and the others are unconstrained. Great, so let's take a look at the math for this. As I said earlier, because this is a fixed recipe problem, we only need one variable per product. So we're going to need 5 variables, right? Call them x1 through 5. x1, how much apple juice you make. x2, how much grape. x3, cranberry. x4, how much of the blend apple grape. x5, how much of the blend apple cranberry. And then we're going to maximize profit. So the revenue is take each of the 5 products, right? 1, 2, 3, 4, 5, times the respective revenue. I'm multiplying that by 128 to get the gallon version of this, because I chose my x variables, right, to be in gallons. So I misspoke. I'm going to get the ounce version of this because these are dollars per ounces, right? So if I tell you if x1 is 10, that doesn't mean 10 ounces, it means 10 gallons. So it's 1,280 ounces. And that number, 1,280, is what I need to multiply by 3 cents, right? Because it's cents per ounce. So this 128 here up in front converts this x from gallon to ounce, so that it's consistent with the dollar value, which is a per ounce dollar value. Great. That's why also we need a 128 in front of the cost expression. How does a cost expression work? Well, it's like this. I pay 2 cents for every ounce of apple I use, but I use apple in 3 places, right? I use apple when I make the pure apple juice. I use apple in the apple grape juice, and I use apple in the apple cranberry juice. So I'm going to multiply 2 cents by 3 things. First, how much apple goes into the apple juice? That is 100% of x1 is apple, because x1 is the pure apple juice. How much apple goes in the apple grape juice? Well, x4 is the totality of the apple grape juice. So I take 70% of that is apple. So this 0.7 x4 is how much apple I used for apple grape. Likewise, x5 is the apple cranberry juice. 60% of that is apple. So here I have amount of apple plus amount of apple plus amount of apple. That's the total apple I use. That I multiply by 2 cents. Similar calculation for the grape, right? I use grape in the pure grape juice, and I use grape in the apple grape juice, but now it's 70% was apple, right? Now 30% of the same x4 is grape, so this is total grape used. Here's total cranberry used. Cranberry costs 3 cents. Great. For constraints, we have availability of the materials, the raw materials. Well, the usage of apple is already here, right? In this parenthesis. So take that, copy it here. Usage of apple, at the most, what I have of apple. Usage of grape, copy down here. At the most, what I have of grape. Usage of cranberry, at the most, what I have. And finally, the minimum production requirements. Make at least 10 gallons of apple, pure apple juice. Make at least 12 gallons of apple cranberry juice. All right, we are ready for the Excel now. Let's go. Here I just made a recipe table to tell me, right, in the columns, I forgot to name them, but the columns are the raw materials, apple, grape, cranberry. The rows are the products, apple, grape, cranberry, apple, grape, apple, cranberry. So this one here means the apple juice has 100% apple, no grape, no cranberry. Same for the grape juice and cranberry juice, and the apple grape juice is 70% apple, 30% grape, no cranberry. So this is just a table that comes from the story of the problem. In gray here are my 5 X variables, how much of each product you made in gallons. The revenue is just data. Here are the cost of the raw materials, again data, below each of them. I'm going to have to calculate the usage of the raw materials, right? Usage at the most what you have, and then revenue, cost, profit. Just copying what was in the math model. All right, so let's begin here. Usage of apple. Well, recall that the apple you use this is how much apple juice you made, right? 100% of this is apple. So this F4 times 100%. Now, there's no apple here, no apple here. Here, there's apple. This is the production of apple grape. This amount times what? 70%. Go back to the math if you forgot this. Is apple. And the last juice, this is the apple cran. If I take this amount times 60%, I get apple. Right? So you might have realized that by now that I'm doing a sum product. I take the recipe, right? And I multiply by this. This is going to say the entirety of juice 1 is apple, 70% of juice 4 is apple, 60% of juice 5 is apple. This is totality of apple. Now, let me dollarize this. Oops. Let me dollarize this part because I want to drag this formula to the right to obtain the usage of grape and usage of cranberry. Okay. Oh, I made a mistake here. Let's take a look. Yes, I can see now I wrote summer product. It's not a product in the summer, it's some product. Okay, so again, the recipe times the total production of each final product. And if I copy this through, we're going to have the equivalent version of this formula for the other 2 raw materials. Great. Now, let's do the objective. Revenue, if you recall from the math, is simply the amount you made of each product times the revenue of each product, right? So I made these amounts. That's what they sell for, but this is all in ounces. So recall from the math, we're multiplying this by the how many ounces in a gallon, right? The 128. Great. Cost. Well, the cost is going to be the cost of each raw material, which is here, times how much you used of each of them, but we already calculated that, right? The usage of apple, grape, and cranberry, we put those values here, if you remember. And like we did for the revenue, we multiply this by the 128 to convert to ounces. And the profit is just the difference. One minus the other. Great. We're now ready to go to Solver. Let's go there. So let's see here. We're going to do, objective will be the cell, profit cell, C18. Maximize. Variables are going to be the gallons made of each product. For constraints, we're going to need the following. The usage of the 3 raw materials is at most what you have of them. And remember, what else did we have there? The 3 usages, right? And the minimum production for the 2 juices, juice 1 and juice 5. So let me do it like this. The productions, right, are at least what you need. Notice that the empty function is a 0, so to say that this variable is greater than or equal to 0 is redundant and it's not going to do anything. And because these are already in gallons and these are in gallons, we're good. Make variables non-negative as usual and change this to the linear simplex solver. And I think we're good to go. Let's see. Solve this. Here we go. So we had a revenue of $4,198.40, cost $1,600, for a profit of $2,598. Notice we are not making any apple grape juice. Maybe, that's a problem for the business. Maybe you want to make some of that because of competition issues and so forth. But if that's the case, you can simply fix this by, putting a number here. What the solver did was essentially just go for the most profitable solution given the conditions that were enforced. We appear to be making a ton of the apple cran juice as well. And in terms of usage of the raw materials, we used it all as expected. And this is it. That's an example of a blending problem with a fixed recipe where you only need to use one variable per final product. Notice, with fixed recipe, you can always revert to the other way and create variables for every combination of raw material and product like you did with a flexible recipe. It would work. It would just be a bigger model, more complicated and unnecessary. But if you want to do that as a form of exercise, it's an interesting exercise and it's possible to do it that way as well. That's it for this video. Thank you for watching. I'll see you guys again soon. Bye bye.